So my plan for today is to tell you a little bit about um, my research group. I'm a professor at the University of Washington, and I'm part of the computer graphics group, where we study next generation design systems. So I want to tell you a little bit about the kinds of problems we're interested in solving, and focusing, of course, on how CAD is important to us and how being able to work with Onshape has enabled us to do really exciting stuff. And then I'm going to conclude at the end with some open problems and ideas. I would love to make this a conversation. I know we're not in person, but please feel free to interrupt me at any time. You can unmute yourselves, you can ask questions, you can type on the chat. I think I'll be able to see it. But yeah, I would love to make this as interactive as we can. So next generation design systems. What are we trying to do? What motivates the research in my group is the novel advances in manufacturing hardware, right? We have 3D printers, we have industrial robots, whole garment knitting machines that can custom make a complete garment. And what that means is that we are about to experience a change in production that is not just about increasing productivity, but it's about, first of all, fundamentally changing the types of designs that we can create, right? So think about multi-materials 3D printers, where you can specify the material properties at each individual part of your shape, incredibly high resolution, right? So now we have objects that can behave differently from anything we've ever managed to design before, right? And in addition to that, it's also about on-demand production. So it's not just about what we can create, but how we make these objects. And what's exciting to us is that because a lot of these machines are versatile, this will enable on-demand batches of one, right, productions of objects. So this is really exciting, right? The ability to create objects that have unprecedented complexity and are designed to fit your needs. But we cannot achieve this with advances in hardware alone, right? Because there's a fundamental step between having an idea of something you want to make and actually going about and making it. And that step is design, right? So the vision of my group, and I'm part of a computer graphics group, is that in order for us to be able to really take advantage of the novel hardware that is going to change production, we need to rethink and reshape design software. And I think about design really broadly, and I've worked on a large number of domains, everything from garments, carpentry, 3D printing. We do a lot of work also in robotics. But for all of these kinds of design tools, we kind of try to think about it and computationally under this abstraction. We think about design as trying to achieve a certain performance goal. So imagine, for example, that you want to design this robot. You need to specify this robot geometry, you need to specify the electronics, you need to specify the control software. All these specifications define this really large dimensional design space. So what does it mean to design from this abstraction? Well, it means to pick a point in this design space. How do we pick this point? We pick this point based on what we want this robot to do, right? How we want this robot to behave like once it's part of the physical world. So is this robot going to walk? Then if so, then how fast does it walk, or how stably does it walk? Or how is this robot going to react to an external force? Or how much money I need to spend if I'm going to build this robot? All of these objectives define what we call performance. So this also defines a higher dimensional performance space. And in this context, and design means to pick a point in the design space based on how it's going to map to performance. Or it means to solve an inverse problem, given some sort of objective that you want to achieve. How do you find the design that achieves that objective? Of course, but think about design as inverse problems, I don't mean that there is no designer in the loop, please. Often how we want is the computer to help solve some inverse problems with assistance, right? So the user can specify objectives. We can guide the user into finding solutions that are similar or achieve these objectives. And there's a lot of user interaction with a lot of the tools we develop. But in principle, underlying all of these algorithms is the concept that there's some space of possible designs, and some algorithms, some objectives that we can express computationally, and algorithms that are guiding the users to finding designs that maximize that objective, whether it is an offline optimization or it is through interaction. So this is kind of the abstraction of the types of problems we are trying to solve. And if you look at this abstraction, one thing kind of becomes really clear. And it is that a fundamental aspect of the first thing that you need to do, before you can start of thinking of your best like optimizers and best ways to evaluate performance efficiently with your physical simulations and all of these cool algorithms that we want to develop, before we even get there, the first thing that we need to define is, well, what is this design space, right? And representing the space of objects that you can create so that you can search is a really important and fundamental step in building these types of systems. And it's also one of the hardest steps, because depending on how we represent the space of designs, right, we might be able to design more things, right, have more diversity. But it also might be more challenging to actually converge to specific shapes that achieve good performance. Or it might mean that the majority of objects on your space are actually meaningless. Right? So thinking about good representations is extremely, extremely important. And there's really no silver bullet. So here are some examples of projects that we'll present next week at a graphics conference, SIGGRAPH. And for each of these, we kind of look and understand kind of the domain and think about what's the right way to do these types of representations. But one representation that we think is fundamental and is used nowadays to model almost every object that we have around us is CAD. So I believe that a really important step to developing design systems and computational tools for the next generation design systems is actually deeply understanding the representations used in CAD systems and how we are going to be able to leverage them in these types of design optimizations and exploration tools. And the reason why I think CAD is so fundamental, actually, when I talk about this, I mentioned something that I learned the very first day of my internship at Onshape in 2016 from John Hirschdick, who I think is here. And we were sitting in this room, and I have this very vivid memory of him saying, "Look around you, and what do you see?" There's this chair we're sitting on. Maybe there's a microphone in the room. There was this box of cookies, because you give cookies to, it used to before the pandemic, cookies to your interns. There's this box of cookies. And the cookies in this box were not designed in CAD, but the box it came from and the machines that were used to build these cookies, all of this started their lives in a CAD tool. And I really took that home, and it's something that I feel like the graphics community since then also has started to appreciate and notice. And it is really exciting that if we understand CAD and the CAD representation, we can actually also understand a lot of the world around us. Right? And also think about the right ways or algorithms that can help us design more and better products, and also make design easier and more accessible to new and naive new designers. So what are these CAD representations? So of course, if you're here, you know this really well, but there are multiple ways to think about CAD in terms of their representations. You can think about CAD as this program, right, that constructs the geometry bottom up. So it's a sequence of instructions, all of which are parametrized. So you have these parametrized programs. You can also represent the CAD geometry in terms of their boundary representations, right? So this CAD BREPs, where you have faces, edges, and vertices, and this connectivity graph. And you could even export this into other geometric formats, such as meshes or point clouds. All of these representations are really important, and working within them and across them is something that we try to do in our group. I want to spend some time today telling you a little bit about 3 projects where we've used these types of representations to solve these types of optimizations and inverse problems. And I want to talk about this in 3 domains. So I want to talk about, first I want to highlight a project that was my first one, working with Onshape, that is about design exploration. Then I want to talk about design optimization, and I want to conclude with recommendation systems that use machine learning. What about design exploration? So one of the exciting things about CAD is that when you think about design as a program, you basically you can expose here in Onshape, we can go and define even variables that we can expose, right, or configurations. And then the user can then tweak these parameters and not and change the shape, right? So a CAD program defines not just one single shape, but a family of shapes. And as a computer graphics researcher, what I would like to do is to take these programs and create systems where now I can optimize, right, within this space of variations to find objects that have better performance. The problem is that searching through this space of families is actually super slow, right? Every time I change a parameter, I need to regenerate the model. And that can be computationally expensive because the CAD kernel is doing a bunch of geometric operations, right? For example, generation times in Onshape for here are some generation times in Onshape for complex models. And you notice that it's, starts to take in the order of minutes once you add complexity. And it's not just about the kernel regeneration time. Like every time you change the parameters, you need to recompute the simulation. So here we're trying to do the stress analysis on this model, and that takes even longer, right? So if you're trying to explore the space of parameters, this can be incredibly slow because you need to then reiterate. So what we propose is to say, well, what if I can give you a CAD model with some exposed parameters, do some sort of cool computation, and then give you back a real-time tool, a tool where you can explore the space of variations in real time. And I can not just explore the space of geometric variations, I can also understand the physical properties. So as I explore this shape space, I can see the stress distribution along this model and then use that to then pick the design that best achieves my needs. I won't go into too many details, but I want to highlight how we solve this problem. Our key idea is to take our shape with the set of exposed parameters and pre-compute some data, basically going back to Onshape, like sampling the space of parameters, calling Onshape and saying, hey, regenerate this model for me. And then we'll store some of these models. And then once we have the stored data, we're going to have some algorithms that when the user says, hey, tell me what the shape looks like at this point, it's going to be able to look at designs that are close by and interpolate in between. So what is the challenge for this? Well, there are fundamental challenges in how you sample this space efficiently, right? And also how do you do this kind of interpolation? Because as you imagine, this interpolated shape, right, is actually, it's not just blending numbers. You actually have to figure out how to morph between these two shapes so that this looks realistic. So I'm gonna, and of course, because once we can do this kind of interpolation, I could also have some other function now on top of this geometry, for example, the stress distribution, and that gets automatically interpolated as well. So our challenges here is that we need a sampling that is, of course, not uniform, so that because different parameters are going to impact the variations in different ways, we want to make sure that we have smooth and continuity across these interpolations, assuming, of course, in this case, that our geometries are not, the topology is fixed across the parametric variations. But a fundamental challenge here is also that how do we then blend or morph between these two shapes, right? If we expose this, for example, as meshes, they are going to have fundamentally different, what we call combinatoric. So they have different triangulations. So how do you actually interpolate in between? A challenge, so the way that we're going to do this, so I'm going to kind of skip the whole how you sample thing, which is kind of some of the more mathy and interesting parts of this paper if you're a graphics researcher, and you're welcome to ask me about this or read the paper. But I want to tell you a little bit about how we're actually able to sample this space and create this interpolation. And we do this by using Onshape. So we used the REST API to do all of our sampling. And one of the challenges here is that when we are going to do this interpolation, we want to have some sort of understanding, right, of how we can do this mapping. Our goal is that if we have a source that has one triangle mesh that we can export and a target that has a different triangle mesh, now we want to find a way to update this source to have a different triangle, a new triangle mesh that matches the target. So we can now have this kind of dance correspondence map between these two shapes. And what we notice is that Onshape actually does part of the job for us, right? Because since these are models that were designed in the same with the same parametric history, Onshape keeps track of references across this design's variations. So what we do is we basically use features. We develop some programs in feature script languages that queries these references for us, exposes them, and of course, we can have some sort of topological variations as long as the overall topology of the shape doesn't change, but the topology of the BREP can change. So we can't guarantee that every single vertex, for example, of this BREP will be there. So we have full correspondence, but we can have some at least partial correspondence in terms of the BREP that gives us a sparse mapping. And then we can use that, leverage this with geometric algorithms that can now help us do this interpolation. So let me show you some results for this. So now here is what you see is these methods where you can now interpolate and explore these design variations. And here you see the stress distribution as I change the parameters of these CAD programs. And what is exciting about this is because once you do this interpolation in the geometry space, I could apply a variety of different physical simulation processes to this. So in these examples here, I am measuring the air pressure distribution along this model, and here I have heat distribution and stress distribution along on this brake hub. I'm happy to pause for questions here. I'm going to move to a different project if there are any questions. All right, okay, so if there are no questions, then I will move forward. Okay, so this was the first project I mentioned was, well, can we explore the space of CAD variations? And then a follow-up on this work, we were looking at ways to now solve the inverse problem. So as I mentioned in the beginning, like in this first problem, we imagine that we have a design space. It's the space of CAD variations. We have some performance that we know how to measure. In this case was, for example, the stress distribution along the models. And we were finding ways to now navigate the design space so that you could in real time see how this object is going to perform. But what if we want to solve this inverse problem, right? Well, the inverse problem is a lot more challenging, right? Because often this inverse doesn't exist, right? There could be multiple points that achieve that performance, or you could be asking for some performance metric that is actually not feasible to achieve. So in this work, we propose to explore, given a parametric CAD model, automatically find this basically the space of optimal trade-offs that we can achieve, right? So if you've done some work in mechanical engineering, you probably heard of this term called the Pareto frontier, which is this landscape of optimal trade-offs when you have multiple performance objectives. The idea here, right, is that there are going to the space of performances that you care about is not your whole space, but only but only the ones that can maximize the best trade-offs across the objectives that you care about. So I don't want to spend too much time on this paper because most of it is actually, efficient algorithms to kind of find this Pareto frontier. The idea being that, this is a really challenging optimization problem because you need to find every optimization problem is challenging, but we're not trying to find just one point. We're trying to find a whole landscape of points at the same time. So, we did some interesting math. We solved this problem efficiently, so that we can find these manifolds at the same time. I don't want to talk too much about it, but I do want to mention this paper because, again, we used Onshape to show that our math is useful in the real world. So I think this is a nice paper to highlight here, because even though the core of this work is, how can we, it's on optimization. Our goal was to make sure that our algorithms could actually be useful for practical applications. And because we had this, because we knew basically how to use Onshape, and we could use the REST API to make these calls to feature script, we were now able to apply these techniques to actual real world problems. So here's an example. We have this brake hub where we have different metrics that we're trying to optimize. So we have forces coming from the brakes, so that impacts the stress. We have mass that we're trying to minimize. We had the heat dissipation. And this was a model from Onshape. And using our algorithms, we can figure out the landscape of possible trade-offs that you can have, and then create this interactive tool where users can explore this landscape of trade-offs with real time updates on what this design should look like. And you see, like, the user here is exploring the landscape of trade-offs on the left, and you see an updated CAD model exported from Onshape on the right. And this was a kind of a really interesting way for us to also learn a lot about our designs as well. So for example, we see these two models that have very similar trade-offs, and this is not intuitive by just looking at the CAD model, but you can see that actually there's the reasons why, like once you have this information, you can analyze it and understand, well, actually there's a reason why you would get the same trade-offs in these two models. So this is what I mean by design systems for optimization. And I want to conclude this talk. The last project I want to talk about, which is the most recent project that my student Ben presented here in our during the process sessions, is a recommendation system. Right, so we talked about different ways of helping users design through allowing them to explore existing spaces, helping them to optimization. And another way to do this kind of interaction with users is through recommendation systems. And in this work, we were looking at assembly. So this is, again, this was a collaboration with Ilya at Onshape. And what we were interested in doing, it was helping users create assemblies. And we do a lot of work on part design as researchers, but one thing that we learned from you guys at Onshape is that actually assembly takes about a third of the time that it's about of the modeling time for users. So we asked ourselves, well, can we create systems and make assembly more efficient? And assembly in CAD is mating between parts. So we call this project automatic mating, or automate. And the idea here is, if the user selects, two parts that they want to mate, right, then the recommendation system is going to say, well, here are some possible ways that you could connect these two parts. Then the user will select the one. The user will then select the one that they want, and then we automatically assign the mates, making the process of mating more efficient. How we're going to do these recommendation systems? Well, we're going to learn from CAD data, right? There are two steps that we need to solve for learning. One is that, of course, we need a pretty large data set to work with. And then we need to find good algorithms, right, that can work with these types with the type of data, with the type of CAD data. So how are we going to do this? So the first step, getting the CAD data, we are going to ask Onshape. And I think Ilya mentioned this already in his talk earlier this morning. But we basically scraped the public collection with Onshape, and we created this data set, which is, again, if you're interested, available, so you can just download it and use it. And it has like a pretty large number of assemblies and mates that you can now learn from. Again, I think this is the first time that a data set this big has been released. And it's really a powerful tool that can allow us to solve a lot of different problems by understanding how objects are composed. The next question we needed to solve then is, well, how do we learn from this type of collection? And I want to go back to what I mentioned in the beginning, which is a problem of representation, right? The past projects, we were talking about the program representations and exposing parameters. But here we no longer have the programs, we have fixed parts, and we want to figure out how we can connect the parts. So we want to learn over the BREP format. So how do we learn over BREPs? So as you probably know, since you work with CAD, a BREP format consists of faces, edges, vertices, and loops. And this is the topological information. And then associated with each of these topological entities, we have geometric primitives, right? So for example, there's a plane associated with this face, there's a circle associated with this loop, line with this edge, and a point with this vertex. So our question is, well, how can we learn, right, using from this format? And the reason why we actually want to use this format and not just, for example, take a point cloud and use networks, for example, that can learn from point clouds or meshes, is that BREPs have arbitrary precision, right? They can capture these kinds of smooth and sharp geometries, but most importantly, the BREPs allow us to explicitly refer to individual parts of the shape. So if I'm doing modeling, right, I am going to say, hey, take this edge and fillet this edge, right, round this edge. So being able to refer to these topological entities is really important. And in assembly, it's the same thing, right? If I want to connect two parts and join them at a given vertex, I need to be able to refer to that vertex, right? So for this reason, we actually really want to be able to learn from the type of BREP format. And because a BREP is this topological graph, we can think we can think about this as just adding a node to each of these topological entities and now defining this as a graph. But how do we then encode this graph so that we can do machine learning on top of this graph? So I'm going to take 2 seconds. This is, I think, the part of my talk that's going to be a little bit more technical. But I want to tell you a little bit about how we can do machine learning on BREP data and why it's hard and how we can solve it. I'm going to keep it high level, but feel free to ask questions. So the fundamental challenge is, so if we have a graph, right, one way that we can learn from graphs is using what we call a graph convolutional networks. So it's basically, think about it as neural networks that can work on graphs, okay? But there's some challenges with working, particularly using these types of networks with BREPs. The first is that in BREPs, you have different types of topology. So you have vertices, edges, loops, and faces. And when we do referencing, for example, for mating, right, we want to be able to refer to all of these different types. This means that our graph is heterogeneous, so the nodes have varying types. And heterogeneous graph neural networks are expensive to train. The other issue that we have is that when we look at this graph, we actually need to understand a pretty large neighborhood, okay, to capture the type of information that we need on adjacency. So say, for example, I have this edge here, this face here that I call A, which is this node in this graph, okay? And I'm trying to understand how it relates to this face here, B. Notice that to get from A to B, I actually need to, even though they are adjacent, I need to traverse 4 edges along this graph because I need to go from the face to the loop, from the loop to the edge to the other loop, and then to the other face. Does that make sense? So what this means is that I actually need to search pretty large neighborhoods when I'm doing learning on BREPs. And this means that I'm going to need a deep network so that I can cover large neighborhoods. And those are pretty hard, okay? They're notoriously hard to train. Okay, so the heterogeneous makes it expensive because these networks are memory intensive, and the fact that they are deep make them hard to train. And in this work, we actually solve this with a couple of insights. The first is that the BREP formats are actually hierarchical. So they are heterogeneous, but they're hierarchical because faces, right, like vertices are going to be connected to edges that then are connected to to loops, and then loops connect to faces. And so if we think about that hierarchically, instead of just thinking, oh, this is a heterogeneous graph, we can now think about this as kind of a sequence of kind of homogeneous graphs when we're going to do this message passing. And this is what we do, and we call this our structural BREF graph neural networks. And I'm not going to go through the details of the networks here, but the key and important thing is that we kind of break it into these layers, right? So instead of having to have these heterogeneous message passings along the network, we break this into a few homogeneous message passings. And then the other thing that we need to do, so then we're going to pass messages from vertices to edges, edges to loops, loops to faces. But then when we get to the faces, that's when the second trick comes into play. Because as I said, like we want to be able to understand the geometry, right? Without having to go deep and back and forth many times. So what we do is we create these meta paths that basically connect adjacent faces, kind of a shortcut. And now because we have these shortcuts, we are actually able to train and learn using more shallow networks. That's kind of the key ideas here. What I want to highlight is this network is really an interesting way to basically learn on this type of collection. And on this type of data, the CAD BREP data. And it can be used in a wide variety of applications, not just mating. Okay, so here is some results of this work, and we show how we can do both recommendations of where to put the mate and the type of mate. The mate location actually works a lot better. This is kind of an example of what a recommendation system looks like. If you look at our predictions compared to, for example, other representations, for example, treating the BREP as a point cloud, you notice that there's a really large jump in accuracy. And what you see here is that by actually working on the type of CAD representation, right, that is what enables us to get that jump. So again, an importance of representation. This also works at a certain level for selecting the mate types, though the accuracy here is not as good. And one of the challenges that we notice is that the reason is that mating is actually quite an ambiguous problem. So here's an example where you have these Lego blocks that you're building, and a user could say, well, these are actually fastened, right? There's no degree of freedom, right? Or you can say, actually, you can pull them out, right? Or you can say that you can pull them out, but you can also rotate. And so we did a little bit of a study where we took some of our examples and actually asked users what types of what mate type you would assign to each of these objects. And we've noticed that there's actually a lot of error and inconsistencies on how users would label mate types, which makes it quite a challenging problem to learn. So I think I'm going to skip some of this and just wrap up so that we can have some time for questions. So here are some of the key takeaways that I would like to highlight in this talk. So the first is that CAD is a fundamental representation, right, as I said in the beginning, if we are trying to model our world. The second is that CAD program variations can be used for design exploration and optimization, right? So if we have CAD, actually CAD programs define not one object, but a family of shapes, and leveraging them for optimization is a really interesting problem. And the third takeaway is that now that we have these great data sets of models, particularly the ones that Onshape is releasing, we can now start to use this data to create better suggestions and recommendation systems or generative design tools as well. And I want to actually, but of course, for each of these takeaways, I think there's still some underlying challenges and areas for future work. So when we say that CAD is a fundamental representation, one thing that comes to mind, right, is that if CAD is how most of the objects in our real world are created, can we use these types of representations to learn about our real world? And in particularly, can we use these representations to reverse engineer, reconstruct, or comprehend our real world? And I think there's some of really exciting work in this domain, working with all of the different representations from CAD programs, BREPs, and these more classic geometric formats in the computer vision literature and reverse engineering literature, some from our group, but from many other groups as well, trying to now use CAD as a way to understand the world. And I think that this is a really interesting area of exploration. The other challenge is that we talk about CAD programs, variations, and how this can be useful for design exploration and optimization. But if you're a CAD user, you know that if you have a design, the minute you start like tweaking your parameters, things typically break. Right? And there's this, beautiful promise of parametric CAD that it gives you this family of shapes, but in reality, once you start editing things, you get these, errors and Onshape of like, this does not regenerate, right? So here is a slide that I usually show to computer graphics researchers, try to explain why this happens. But I feel like, for a CAD audience, it needs no introduction, that this is a fundamental challenge. So efficient ways, right, to enable these explorations by enforcing that the object is still the right program. I think this is a really interesting and important question. So this is something that my group is working on, and this is a paper from this year, kind of a first step towards can we do these kinds of direct editing and modifications in CAD by doing program optimization and understanding the boundaries of these programs. So here's an example with the user's editing, and we are regenerating programs. Though there's still, a lot of research, and this is, I know that other groups are also working on this, but I think this is a really interesting and important area for design optimization within program domains. And then, of course, there's the question of leveraging CAD data for designs. I think there's interesting work on the right. Yes, we were using Blender for that project. Yes. More for, but we will, the next one we'll use Onshape. And then the other point I want to make, and I think it's something that came up in the posters presentations as well, is that we there's a lot of excitement right now in the machine learning world, and how can we use CAD data, right, to perform different tasks. And we're really excited about this in our group. But one of the things that we notice also is that it's actually not trivial to work with real CAD data. There's a lot of noise. There's a lot of missing labels if you look at Onshape's public data set, right? And not only that, we have a lot of problems that are ambiguous, like the mating problem that we mentioned, right? This is an ambiguous problem to begin with, right? So I think that there's, so I think one area that we need to work together to solve is how can we work with these collections, and what's the right trade-offs about understanding ambiguities and our engineering insights and data-driven methods, so we can actually leverage these collections in good ways to solve real-world problems. So that's it. That is my talk, and I will thank you for your attention. And I'll love to take questions now.
Awesome. Thank you so much, Adriana. I feel like my brain has grown 12 sizes, and I especially just the visualizations, the graphics that you were able to use to explain these concepts that are well over my head, at least. I feel like I was able to understand the basic building blocks of some of these, very, very complicated concepts. So yes, please feel free to put questions in the chat, or you could even raise your hand and I can allow you to unmute yourself, turn on your video. But maybe I can start with one question, which I think is along the lines of what you closed with, which is that these problem spaces, the products that are being designed, there's no constraints and everything is very ambiguous and ultimately driven by the intention of your design and the real world problem that you're solving. I would design one way if I was 3D printing it. I was design another way if I was using some other manufacturing method. And my question for you as a researcher is, to what extent is your next project guided by some real problem that someone brings to you versus some technology that you see there's a new opportunity that is untapped? And how do you, take that balance and find the right project in the middle?
That's a really good question. So I think that the projects that I like to do are things that are at the intersection, right? I usually like to look at problems that I find exciting. And for me, that typically means that they have a good application, right? That they can actually be useful to solve real world problems. But I also like to solve problems that I will be good at solving, that my group has the knowledge and the techniques and the skills to actually address, right? And a project that is at the intersection of these two things are the right projects for our group. So typically we try to find projects at this intersection. That said, as a professor, I usually just do whatever my students want to do.
Yep. As we said going to the poster session, they're the ones that actually do the work.
That's right.
So yeah, that's great. So we had a question from Allison Olachowski, which I think is along the same lines, but that question of what it really means, real world design. So if you want to elaborate on that a little bit.
Yeah, that's I think we use this, maybe I use this term in two ways, right? So I think about real world designs first, designs that were actually created by engineers and designers, right? So for example, the CAD data, I assume that, the models that are there were designed by engineers. So I want to learn how engineers design, for example, for the mating problem or the recommendation systems. And we want to use real data because we want to, if we want to help generation, or if we want to help, make suggestions, we want to do that based on the way that people are creating designs. The other thing that I sometimes mean is, designs that we use for fabrication. So designs that can actually be manufactured and produced, right? That represent the objects in our real world. Now that said, a lot of the times, in order to make advances in research, we need to kind of scale back, right? And work. So a lot of the most exciting projects, some of which again were presented during the poster sessions, that can do, generative CAD designs, they're actually looking at really simplified models, right? And models that only use a few of the primitives. And I also think that this work is super exciting because, in order to take the first few steps in advancing the technology, we need to start solving the simpler kind of toy problems as well, right? But there is a fundamental gap into taking also these technologies and pushing it to, the actual fully blown like CAD systems, right? And I think that that's really an exciting area for research as well.
Cool. Yes, certainly have to crawl before you can walk, before you can run.
That's right.
Great. And yeah, I think we're at the end of time. My next question was going to be, John Hirschdick's comment about everything around you in the room being started as a CAD design, but everything out there in nature is not started in CAD. So how do we represent biomimetic designs, which is a new frontier in design in CAD. But that's the running phase maybe, and where we're going.
I think there are a lot of things that we can learn from CAD when we are trying to, for example, design materials, composites, or even proteins. I think there's some interesting knowledges there. So in terms of the representations, so CAD uses programs, right, to represent designs, and programming languages and domain-specific languages for design can be applied to many different domains that are not just CAD. And the technologies that we develop in programming languages for CAD can be applied directly to these other domains. The idea of using graphs as well, right? BREPs and graphs, we can share this knowledge. Again, like a lot of the graph neural networks types of work was actually started from molecular biology. So I think that there is a lot of, I think, kind of these abstractions of thinking about designs as programs, thinking about designs as graphs is something that spans a lot of other disciplines as well.
Cool. Great. Yeah, it's such exciting work. And yes, thank you again for the very informative presentation. Again, I feel like my head has grown so much.
Yeah. Well, thank you for having me. It's really a pleasure to be here.